I want to welcome you to today's lecture. We started chapter 11 the other time, where you've been introduced to our linear statistical model. Okay, I introduced you to that on Wednesday. And of course, today, we're going to continue from there. We want to look at method and properties of least square estimate. Of course, before now, actually introduces to statistical linear model, okay, situation where we actually want to characterize a relationship between variables. And of course, I show you model specification with some parameters in them. I was able to show that the expected value of y is not equal to constant, actually depend on variables and parameters. And what we want to do today, I'm going to say it's another calculus, and I need you to pay attention. Okay, so how do we, when we have parameters in our model, okay, how do we estimate that? Okay, of course, I'm actually going to walk you through the method of least square. Okay, the method of least square. We use method of least square. Not only method of least square, we also use method of maximum likelihood to estimate parameter in linear model. But what I'm going to walk you through today is how to use the least square method. Then let me tell you this: whenever whenever estimator is involved, we also, just like what we did before, where we investigate how good our estimator is, we're also going to investigate that here too. So we're going to look at and that was what I call properties of least square estimate. We want to be able to see whether they are unbiased, whether they are efficient, whether they are consistent, just like what we did before this topic. Now I need you to pay 100% attention to what we want to do now. Now, I want to start with the method of least square. But before starting with the method of least square, I will need to first show you the model. Of course, what you can see right now, I told you the other time, this is the model. This is the way we specify the model. It's like assuming a straight line relationship between y and x. Y is dependent, x is independent, and of course the parameters in the model is beta naught and beta 1. Those are the parameters in the model. Then when you take a look at the model now, you're actually going to see, let me tell you this side. What do we call that side? That's a deterministic part of the model. And what about this guy? That is a random part. Every statistical model specified, we have both deterministic parts and the random part. So the random part is the error, and that is a gap between the model and reality. If reality is y, okay, if reality is y, okay, and the model is beta naught plus beta 1s, then the gap between the difference between y and that is going to be the error. I told you the other time, model is not going to be the same as reality because there's always going to be a gap. We acknowledge that, and what we're trying to do is to minimize that. Now, when you take a look at what we have here, okay, getting this guy now, it's like, okay, you know what? When I take the expectation and I find the average, okay, because expected value of error is, we're assuming that to be 0. Let me tell you this. That is one of the assumptions. Moving forward, okay, if we don't make that assumption, there's no way we're going to move forward. I told you the other time, bias any simplified assumptions made in order to make our target function to be easily estimated. If we don't make assumption, there's no way our target function can be easily estimated. So, and that is the reason why we are assuming now expected value of error equal to 0. It may not be, but we have a way to investigate. Okay, and because that's going to be one of a way to validate our model, okay, to see whether assumptions hold. And I told you the other time, assumptions in a linear model revolve around the error term. Okay, when the assumption hold, we're going to say error behaves well. Does that make sense? Okay, now when you take a look at the linear model now, okay, this guy and this guy, we actually call them parameters. Those are linear regression parameters. The beta naught and the beta one. The beta naught is the intercept and the beta one is the slope. Now, they need to be estimated. Okay, so now if you take a look at this guy now, because we want to obtain this parameter using sample information, then they're going to have a cap. Now, because of that, they become estimates. Okay, so which they're going to have a formula which we're actually going to call estimators. I told you the other time, when parameter estimation is involved, of course, you actually need an estimator. So we believe that the moment we have a beta naught cap and a beta one cap, and we plug in back into the model, okay, and that is actually going to be an estimate of the average of the response we're looking for. Does that make sense? So this guy now is actually going to be equal to expected value of y. Okay, so that is exactly what I mean. Okay, so I told you the other time, if you actually go into a population, we're actually going to get bivariate data. Okay, don't forget, we maybe x may be let's visit company. Let's go to production company. Maybe x is production quantity. Okay, production quantity. Maybe that's our s, and y is production, let me just say runs time. Okay, runs time. Okay, so we actually want to study relationship between runs times and production quantity. We actually want to see the effect of quantity on runs time. Of course, we're not going to use all data set available in that company. We don't have time. We can take a sample. That was why you see that as a set of n data point. Okay, and before we can think of the kind of model that would be appropriate, well, based on what I show you on Wednesday, we got different kind of models, right? I think I show you the linear model, I show you quadratic, I show you exponential. There's so many of them, and the only way to make a sense of what the model we're going to specify, we actually need to generate a scatter plot. Okay, a scatter plot is a diagrammatical plotting of y against x. Okay, of here production quantity against the runs time against production quantity. Now when you plot that, you actually, even though we don't, for it to be a straight line equation, we don't expect a perfect straight line. There's gonna be some point that actually gonna be scattered away. That's why it's called a scatter plot. Okay, and if you take a look at this straight line now, that is the line of best fit, or I'm actually gonna call that the line of equal distribution. Okay, and when you take a look at this guy now, you know, if the points are far away from the line, that will show a weak relationship, but we normally want situation where points will be very close to the straight line. And I need you to take a look at this now. Take a look at this guy. Okay, I have a y cap and I have a y. There's a difference between a y cap and a y. The y is the original. Let's say y is the actual runs time, and the y cap is predicted runs time. Maybe we already know this guy. We already we know our beta not cap, we know our beta one cap, and we plug in production quantity, and the model actually give us a predicted value for runs time. Okay, so the difference between the actual value of the runs times and the predicted value of the run time is what we actually call error. Okay, and you know what? That very error, we want to try and minimize it, but no matter how we do, even using the best approach, okay, anywhere in the world, that error can never be zero. Okay, there's always going to be error, but on average, we're expecting it to be zero, not individually. Okay, so that's what I mean. Now, if we now want to seek to, we're actually going to have a way to minimize drastically the gap, the error. Okay, if I want to estimate the parameter, like if I want to get a beta naught and a beta one, I actually need to seek a technique that puts into consideration minimizing the error, and that's why we call it least square. Does that make sense? Now, I need to take a look at this now. Okay, this are the parameters, and this will be the estimators, just like what we normally do before this topic. We were focusing on a probability distribution that have a parameter, and at the end of the day, when we specify our estimator, whether we derive the estimator through sufficient statistic or method of movement or Nehmer Fisher factorization or whatever, or method of maximum likelihood, of course, we actually have a way to get our estimator. So here, we also want to figure out what the estimator is going to be, because if I want to measure relationship, then the parameters in the model need to be estimated. Okay, now this is the model. Okay, why am I putting y? Why am I putting a cap on y? That very y is going to be a predicted. It's not going to be actual y. Okay, what model predict? But we can only have a predicted y if we already have a beta naught cap and a beta one cap. Okay, and I told you, if you take a look at this guy now, right? That is a gap between the actual response and the predicted response. Does that make sense? Okay, and let me tell you this. If I have, let's say I have 50 observation, then it means I'm going to have 50 errors. Does that make sense? Because on each response variable y, I'm actually going to compute a corresponding predicted y. Then when I subtract that, I'm actually going to have this error. And let me tell you this. When I have this very error now, it could be negative or positive, right? Now, if it's going to be that, but I just want to prove to the world, okay, whether negative or positive, I want to prove to the world that -3 and 3 is the same. Okay, because if I'm going to tell you now, if this is 0, okay, the distance from here to here is the same as the distance, and because of that, if I want to prove to the world, I'm actually going to say -3 squared is 3 squared is 9. And that is why we're talking about something squared, okay? And least means we want to minimize the square. Now, I needed to pay attention to this guy now. What am I doing here? I'm squaring each error. Then what am I going to do now? Then I sum them. Now, summing them, please, I needed to pay attention. A calculus is going to come in, but do you know that when you make a sense of the calculus, it's just going to be easy? Now, You need to first understand what are we doing here first. Go ahead. Oh, that's a very good question. Why can't we take an absolute value? Why squaring? Because even though we know absolute, the absolute value of -3 and 3 is actually going to give the same, we are squaring because we want to use the idea of the variance. You remember in variance, what it comes with square, right? And you know, and when you take a look at something squared, the derivative will exist. Does that make sense? Something square when you differentiate, okay? Because we're going to use optimization because we really want to we want to minimize. Okay, so now you understand that. But uh, we got some area in statistics, not this, where in terms of metrics of evaluation, where we use absolute mean square error or mean square error. We got situation where they consider that too. But here we actually want to use the notion of the variance, and that is the reason why we're considering the square distance instead of the absolute distance. Does that make sense to you now? Okay, now what is the meaning of this? I need you to pay attention. I understand my statistics and mathematics excellently. You know why? Because I know what is behind every notation. Do you know the meaning of this? We call this sum of square error. It is called sum. This is like totality of unexplained variation. You know, uh, we believe that um, we want to explain variation around y, around the response variable y. Like here now, we want to explain variation around runtime. We believe there's going to be a total variation associated with runtime, and we want to be able to see out of the total variation here, how much can production quantity explain. Okay, then the total variation is actually going to be equal to explained plus unexplained. There's always going to be unexplained no matter what we do. So this is the sum. This is what we call the total unexplained variation. That is the variation our model cannot explain. Does that make sense? Okay, now we want to plug in y cap. What do we call y cap? The y cap is a feed is a feeder model, right? Then I'm plugging in y cap. What do I now plug in y cap now? You know what I'm gonna do? I actually want to figure out what is gonna be the optimal value for the beta null cap and the beta one cap in such a way that this guy will be what? Minimized, because we want a situation whereby the total unexplained variation will be minimized. When the total unexplained variation is minimized, then the explained will be maximized. Does that make sense? That's exactly what we want. Now, because of that, we're now going to borrow an idea in mathematics that we call optimization. You can see now. Okay, so that is what we're going to do. So we're going to borrow an idea from mathematics that we call optimization, which means I'll come and differentiate this with the respect to beta naught. Then I equate it to 0. Then I solve for beta naught. You see that? Then I'm going to do the same to beta 1. I'll differentiate it with respect to beta 1. Then I set to 0. I solve for beta 1, which is exactly what I'm doing here. Take a look at this guy now. You can see we don't just do calculus. We got a reason why we're doing calculus. Right here now, what have we just done? We've differentiated the sum of squared. We are optimizing. That is what it means. Our optimization here is minimizing the sum of square error, okay, which is a total unexplained variation. Now I differentiated with respect to beta. Can you see? Can you see now? That is the way we differentiated with respect to beta. Okay, then we equate that to 0. Now when we equate that to 0 now, okay, we start simplifying. Let me tell you this. I'm going to tell you now. Calculus, 95, to the best of my knowledge, 95, at least 95% of what we do in mathematics is algebra. Because inside calculus, we do algebra. Now, take a look. Do you understand how we get to that junction, the one I circled? Go ahead. No, we're going to do it one at a time. We do for beta 1. We're also going to do for beta naught. Does that make sense? Okay, now, after getting that guy now, we now want to solve. Okay, we want to simplify. Okay, what are we looking for? We are actually looking for beta 1. If you take a look at this, let me first show you this. If you take a look at where we are here, okay, we want to solve for beta 1, right? And don't forget there is still beta naught cap. Can you see beta naught cap part of that? Okay. Now, if you see beta naught cap part of that, so what we actually want to do is to see, if you take a look at this guy here, you can see that, right? Okay. Now, I'm actually using that. It's not necessarily that you follow all this one. You can have your way of doing it. Now, let me just tell you what you can do. For this one, if I want to substitute for this guy, do you know that y bar equal beta naught cap, okay, plus beta 1 cap x bar. Now, from here, what do you think my beta naught is going to be? Okay, so like I said, we have that relationship. We got y bar equal beta naught cap plus beta 1 cap x bar. So what is beta naught cap? Y bar minus that. Wherever I see this guy, I'm actually going to put that guy. Okay, you may not go by day. If you see following, if I put this one now inside the beta naught cap, all what I'm just going to do is to solve for beta 1 cap. Solving for beta 1 cap, you're actually going to find yourself here. Okay, you're actually going to find yourself here. Take a look at that. Okay, so this is beta 1 cap, which means if I want to get from data set, if I want to get beta 1 cap, I actually need summation xy. Don't forget, I'm actually going to have my data set is going to look like this, right? I'm going to have some data here, where I can get xy, s squared, y squared. Then I just need a total. Summation s, summation y, summation xy, summation s squared, summation y squared, the total. Okay, so that's how we derive the estimator for beta 1 cap. Don't forget, we actually make use of this relationship. Okay, and the moment you're done with that, okay, because we already know, even if you try something, because some of you may be wondering, how do I know that guy equal to that? If you start from beta naught, maybe you 4 of us try and differentiate this guy. I'm going to do that for you. So you're going to see now, okay? You can decide to 4 of us start differentiating first with respect to beta naught, okay? If I, the sum of square error equal summation y minus beta naught cap minus beta 1 cap x bar all squared. Okay, so I start from 1 to n. Sorry, this is yi. Okay, so just like what you have there, when I open the parentheses, gonna be that. Now I want to differentiate this guy now with the respect to beta naught. Okay, with the respect to beta naught, okay? This is a composite function. I'm actually going to have two, okay? Differentiate that -1. Then I'm going to have summation I star for 1. Then yi minus beta naught cap, beta 1 cap x bar, and that will be 1. This is a composite function, okay? And I'm going to equate that guy to 0. Okay, divide this is going to be a -2, right? Divide both sides by -2. So I'm just going to have yi this. I think when I start, there's no that guy x, okay? Because the module is beta naught beta naught plus beta 1x plus the error. Okay, and if you take a look at this, it's more or less like error equal to this, right? This is error. And another way to write this is to write summation error I squared, because it's the sum of the error unexplained. So here now equal to 0. So summation times y, summation yi, summation times this, it's going to be a constant at the end, that minus summation times that beta 1 cap summation si equal to 0. So this is going to be summation yi equal and that plus summation si. Okay, divide both sides by n. Okay, this is going to be y bar equal beta naught cap plus beta 1 cap x bar. You see that? Okay, y bar equal to beta. So that is how we derive it. So in the end, if you take a look at this guy now, okay, what are we telling the world? And let me tell you this before, we actually got for beta 1, this is the expression. We can also write it this way. And we can say the top one, the numerator is covariance. Covariance. The denominator is the variance, like sum of square deviation for x. Okay, that is why you say this. You can also the estimator now is this. We're trying to say, okay, the beta naught cap and the beta 1 cap equal to that. So those are our estimator. Okay, now if those are our estimator, okay, so I'm actually going to say, okay, the beta 1 cap is that the ratio of covariance to the that where I'm trying to say SSY is that and SS is that. Okay, so that's what I mean. So which means another way to write summation x minus x by y minus that is to write SXY subscript, and the other one with that focus on S, it's just gonna be SSS. Okay, now which means if I have data set now, okay, if I want to obtain the beta naught and the beta 1, then this is what we're going to use. These are estimators. Okay, now if those are estimators, let's take a look at data. Use the method of least square to fit a straight line to the n equal to 5 data point given. You got this x and y. Okay, and if you have this x and y, what you're going to do first, you actually need additional column. You have x and y, you use a calculator. What is xy? That stands that. So you get xy, then you get s squared, then you get the total. Okay, the moment you get the total, you want to get it beta 1, right? Okay, now you want to get it beta 1. You can actually see here, okay, if you go back to the formula, okay, we want to use okay, we want to use this guy now. Okay, now sum of xy, the sum of xy, the sum of xy is 7. You see that, right? The sum of x, y, 7. Okay. And then the one that talk about the mean, the mean of x is going to be this guy divided by the number of data. The mean of y is going to be this guy divided by the number of data. And, by the time you actually apply that, that was how we got this guy. Is there any question about how we got beta 1 cap to be that? Is there any question? Go ahead. Okay, so you mean x bar? Yeah, that is why there's 0 square here. This is 0 square, right? Yeah, because if x bar, if sum of x equal to 0, then the s bar will be 0. Then the s bar square will be 0. So if you take a look at the formula here, you can use any of that. But if you use this, it's still going to be okay. Let's see now. Let's start plugging in. Give me 1 second. You're going to see something right now. Okay, so let's see. What is this? What is sum of xy? That will be 7, right? Okay, let's go back and plug in 7. Now, if you take a look at this, n x bar y bar, if you come back here, sorry, if you come back here, x bar, this is going to be 0, right? Y bar is going to be 1, but because n multiplied by s bar y bar, s bar is already 0, that's this area. Sorry, this where is it? Okay, this area here is actually going to be 0 based on what I just said right now. Then what is the summation s squared? We're going to go back to the formula, to the data. Okay, 10. You see, summation s squared 10, right? Okay, summation s squared. Okay, this guy is actually 10. Okay, now n s bar squared, because s bar is 0. So that would be 7 over 10. So what is 7 over 10? It's still 0.7. That very beta 1 cap, there's so many versions of it that's still going to give the same result. Does that make sense? The only thing, you just spend your time, understand the formula. You can use any of that. There's no problem. Okay, so now the moment you get your beta 0 or your beta 1, it will be very easy to get your beta 0 because, but let me tell you this, the moment your beta 1 is wrong, your beta 0 will be wrong because you can see inside the beta 0 you have a beta 1, right? Okay, so with that, you actually have that. So which means right now we've gotten the beta 1 to be 0.7 and beta 0 to be 1. We're still coming back to the interpretation. Okay, now you know what we want to do now. Before we can rely, let me tell you this. I'm gonna quickly tell you something now. This guy and this guy, they are least square estimators. I told you estimator is a formula, right? But this guy, the result that we got are called least square estimates. There's a difference between estimate and estimator. Estimate is a particular value assumed by an estimator. So in statistics, we don't pay more attention to estimate, we pay attention to estimator. If estimator is wrong, estimate will be wrong. And because of that, the next thing we want to talk about the properties of a good estimator. Just like what we did the other time. We want to look at the properties of a least square estimator. Does that make sense to you now? Okay, statistics is a story. Okay, yeah, and the story goes on and on and on. Now, if I want to seek a relationship between variables, particularly two variables, okay, of course, these are the steps. I need to specify my parametric module. Then I fit the module to the data, trying to get the optimal value of the theta by minimizing a cost function. Do you know that sum of square error is also a cost function? Because error comes with costs. I think you know that. And that's why we're trying to minimize. The same way we minimize cost is the same way we minimize error. Then after deriving our estimator, the next thing is quantifying how accurate, they are. And if I want to know how accurate they are, then I need to look at the properties of a good estimator. Oh my God, if I want to look at the properties of a good estimator, then it means I need to investigate for unbiasedness, the consistency, efficiency, what we've done before. But we need to, for us, remind you that this is a specification of a model where we assume that the expected value of error equal to 0 and the variance is sigma squared. That is what we call variance of error. Sigma squared means that is what we call that homoscedasticity. So that is a constant variance. Okay, we call that homoscedasticity. Okay, that's a constant variance. Okay, so we're trying to say the variance of y given x. Okay, or it's going to be constant, and not only that, the variance of the error, okay, given any values of s is actually constant. And of course, these are the optimal estimate that we derive. Now, if I want to investigate how good is an estimator, I have to first investigate for the unbiasedness. We need to prove that expected value of beta naught cap equal beta naught. We're also going to prove that expected value of beta 1 cap equal beta 1. Then we also need, because we actually want to evaluate their efficiency, then we need to be able to derive their variances. Why are we deriving their variances? Because we're going to show their unbiased. When they are unbiased, then we need their variances. When they are biased, we need their mean square error. Okay, so now I'm showing, I just first want to show you, telling you now, they're going to be unbiased, and I'm going to show you how. And we need their variances. Then these are the expressions. We need to derive the expression, and we need algebraic knowledge here. We want to show all this. That is why this course is called Theory of Statistics. We need a lot of mathematical knowledge, to be able to derive. Now, what I want to do now? Let's start with unbiasedness property. Okay, please pay attention. Now, there's some things we need to note. If I want to start, I want to start from here. I want to show that estimate of intercept on average is the same as true intercept. There's a true intercept. There's an estimate of intercept. Now I want to show that. And for me to show that, I first need to tell you sum of deviation equal to 0 without square. Okay? And if the sum of deviation equal to 0, how? Then you need, if you know that this happen, and which is what is happening here in the data. Anytime you do, for instance, if you have x and you find the mean of x and you subtract the mean from each of that and you add it if you add it, it's going to be 0 all the time. Okay? Now, if that is 0, if that equal to 0, then I need you to take a look at this. And I want to work with the one that have to do with square. The first one that is equal to 0 does not have to do with square. Please pay attention. If you don't understand, ask me a question. Oh, wait a minute. Am I talking so fast? Is there anyone in this class who is actually getting a trouble time understanding the way I talk? Is there anyone? Is there anyone? You all understand the way I talk, right? Okay, thank you so much. But you know what? Do not hide your feeling. Now, moving forward, we make a lot of assumption. We can write that as this. Okay, the one reciprocal that we can write like that, and therefore this we can write it as this. What is happening? Xi representing x minus x bar, yi representing y minus y bar. Now, without making this assumption, we may not be able to show the unbiasedness property of the least square estimator. Now, let us now start it. We want to show that the expected value of beta 1 cap is beta 1. Okay, and we derive beta 1 to be this the other time. The SSS is summation. I'm gonna write that. Okay, X, this is this, right? And I said right now, this can be written as this, right? Okay, now, please, I need you to be focused. Now, if you take a look at this now, I can rewrite, if you take a look at this, I can write it as this. That is what we assume here. Any question? Okay, do you see that now? Now, expectation multiply. I want the expectation now to multiply them. Expectation is only going to grab y because that is the response. That's what we want to explain. Now, if that happens, please pay attention. I'm actually going to have this guy. What has happened now? Expectation has grabbed y. Does that make sense? What does expectation of y equal to? Expectation of y equal to this. You know that? Equal to beta naught plus beta 1s without error, because expectation of the error equal to 0, right? You see what I have now? If I have that guy now, the only thing you need to do is to simplify, right? Use beta naught to multiply that and beta 1 to multiply the other one. We're doing algebra now. There's no calculus right now. Where I'm actually going to find myself here. Is there any question? You see that? Just use that one to multiply. Oh my God, I'm seeing something now. Take a look at that. We said this equal to 0, right? Okay, what is going to happen here? That's going to be 0. That will nullify beta naught. Does that make sense? Now, and that was why you see here, you see that we plug in 0. Okay, so what are we left with? Okay, now we're only going to be left with this guy and this guy. Oh my God, what is SSS? It's the same thing as this guy. So this guy is gonna cancel that guy. What are we left with? Beta 1. We proved that. We've been able to prove that expected value of beta 1 cap equal beta 1. We show that on average, the beta 1 cap is equal to the true values of beta 1. I'm actually going to stop here because of my time. I'm going to use this material again on Monday before going to the next. I think the Monday material is also about properties of an estimator. Okay, any question before I go today? So finally here, this is showing that expected value of beta 1, expected value of beta 1 cap, okay, equal beta 1. That is what, so what we just did now is to show that beta 1 cap is an unbiased estimator. So what we're going to show next is this guy. Also to show that beta naught cap is also an unbiased, if you follow all of that too. So, but we're going to start from here next time. Then after that, we go to the variance, we derive the variance and do some other stuff, okay? Make sure you all stay safe and have a lovely weekend. If you have not grabbed your exam document, you can come for that right now. Okay, give me 1 second. Let me just, okay, yeah. Okay, so let me see. Okay, one more bar. No, not squared. Let me show you how is zero. You're gonna see now. No, you're gonna see now. This, right? Uh, multiply that, right? This is a constant, right? This minus, what is this? Summation x over n. That is it. Which one? No, the one with square can't be zero. It's not possible. No, this one is not squared. The first one. Do you know this is the one we just give me 1 second? This is the one we just derived now. That is what gave you zero. Yeah, in the next one, if you take a look at this guy, I will rewrite that as no, you will see something now. I can rewrite that as right. Then this is another variable. I can just call it a new variable x. So that I'm actually going to write this as this. Yeah, that's another way. If you then you are talking about summation s squared, which will be sum of deviation. But this x here is a star, not the original s in the data. Yeah. Which one? No, you mean is it this one? Why can't this one be zero? No, it cannot because of a summation here. It can't be zero. Yeah, because this first one is just you have this only. Yeah, the random variable is only here, and this is giving zero. But here, the random variable is here is also here. If I expand this, you know what is going to happen? Let me expand this and see. X squared minus 2x bar x plus x bar squared. Then when you continue to go, 2x bar, summation x plus n s bar squared. So summation s squared, this is going to be 2x bar, and this guy is n x bar plus s bar squared. What do you have? Summation s squared n s, which is summation s squared n summation x over n. You can say it can never be zero. Do you understand? So it's only the first one, sum of deviation is zero, but sum of square of deviation, never. You welcome? Yeah. Let me end this. Give me 1 second.